This is the model that we have been talking about before. That's the gated MRF, where these gray nodes are the pixels. We have a factor node that connects twice the pixels and to the hidden variables here that are called covariance latent variables. And then we have another set of latent variables, the mean latent variables that also connect to the pixels. And these mean latent variables set the biases for the pixels, while these latent variables set the kind of correlations between every pair of pixels, right? I built a data set of image patches from natural images from the Berkeley segmentation data set, something like 100,000 image patches, color image patches that were whitened. And then I run the learning algorithm that I described before, where I need to run hybrid Monte Carlo at every step to compute the gradients. And after training, I can look at the parameters that I learned. So I'm sure that in this couple of weeks, we have seen many, many filters, and they all look like gabors, and yet another one. So these are the mean filters. So these are the parameters that connect the mean latent variables to the pixels. And every tile here corresponds to one column of that matrix W. So that then are reshaped into a square patch that has the same size of the input. And you can see that many of these filters end up being kind of gabors, but there are also many blobs, these white spots, and color gradients too. If we look at the covariance filters, the filter bank that is here connecting the pixels to the factors, again you get gabors. And now I initialize the matrix P to induce a 2D topography. So basically, matrix P I initialize is a banded matrix and initialize in that way, so that each latent variable is connected to a small neighborhood of filters that in this map here. Okay, so that's done by hand. But then I let P adapt. So although nearby filters tend to be similar, sometimes I allow for through learning nearby filters to be also different if they want to do so. So all these filters look like gabors, right? But what they mean very different things. Because a gabor here, for instance, let's take this gabor here, is saying that pixels on this side of the edge tend to be strongly correlated with each other, and pixels on the other side of the edge tend also to be strongly correlated, but there is no correlation between pixel on the other side of the edge. Why, if we look at these filters here, this is that a gabor here says that here, a pixel here tends to be darker than a pixel here that tends to be brighter. So this is about mean intensity, while this is about correlation. Okay, so although they look similar, but they do very different things. And a way, yes.
So going back one slide, what did the single color covariance filters do? Like the big orange one or the big purple one?
These ones.
Yeah, like what did they do?
They have a small gradient. It's very faint. Because filters are normalized, so if they are localized, then you see them very well. If they are global, you don't see much the gradient, but actually they do have a gradient. You wouldn't expect to find totally smooth, totally uniform patches, because they should find something like the minor components. So that would be kind of surprising indeed. Now, a way to interpret the model, besides looking at the filters, that is, it's what it is, is to draw samples from the model. Because this is a generative model, so you can draw samples. And you can draw samples in two ways. One way is to draw sample from the marginal distribution, P of x, and the other way is to draw samples from the condition distribution, so P of x given the latent variables. And this is exactly what you're looking at. So I took some image patches, I computed the latent variables, and then, given the latent variables, the input variables are generated from a Gaussian. And now I'm doing a random walk using this Gaussian distribution. And every frame here of the movie shows a different step of the Markov chain sampler. Okay? And so you can see that basically, as you sample, you can see the whole subspace that is mapped into the same set of latent variables, because the latent variables are fixed. And so you see that you get variation of color, slightly variation of the position of the edges, a little bit of distortions, right? The other thing that we can do is also generate from the margin distribution of the input. That is perhaps more natural. So here on the right, we have natural image patches that I use to train the model. And on the left, we have samples generated by different models. On the top, the model that I have described. So every tile is a sample. And here are samples from a Gaussian RBM. That is, basically, if you take my model and you remove the covariance latent variables, you would get samples like this. While these below are samples from a so-called semi-restricted Boltzmann machine that is with many layers. Well, these models have just one layer. And basically, this SRBM is a special RBM where they have lateral connections between the hidden variables, while I have lateral connection in the pixel space. And as you can see, the model that I propose is able to produce, by visual inspection, samples that look more natural, more similar to actual images than previous models. And of course, you can quantify this by estimating the probability and things like that. But it is also good to have a gut feeling of what these different models do. Let me, before I go ahead, let me mention another issue, that the results that I'm showing, that everybody shows, are strongly dependent on what kind of preprocessing you do on the input images. And there is a standard preprocessing, which is whitening. So if you think about, before I mentioned that this model has an energy function which takes square filter outputs. And so in some sense, you're looking for directions of minimum variance. And so you're going to discover a nonlinear version of the minor components. And therefore, if you don't do any whitening, you're going to discover very, very high frequency things, because it's looking for things that pretty much never appear in the input. And therefore, by whitening, typically people cut the very high frequency, and then you get to model the minor components in a limited spectrum where things are kind of localized and Gabor looking. So that's also why you always get Gabors. It depends also on how you preprocess. But the other key element is mean subtraction. So one question is, why do you need to model the mean intensity if you can just take it out from the input and forget about it? So to answer this question, I prepared this slide. So here, on this panel, we have image patches that were normalized by subtracting the mean intensity, so the average pixel value, from every patch. So if you take the average of all the pixels in this little tile, you get 0, as well as here. Well, here on the bottom, we have that the whole set of data points has been centered. So I subtract the same number from every single image patch. So each patch can have a non-zero mean. Now, if you take 2 pixel images, so if you take images of 2 neighboring pixels, and you draw the histogram, and you preprocess the images by mean subtraction, every data point you subtract the mean, you get a histogram like this. So basically, most of the images are at the origin, or very near the origin, because most likely nearby pixels take the same value. But sometimes, you have long tails on the anti-diagonal, which is when you have an edge, when pixels take different values, right? If you don't do the mean subtraction, you get a histogram like this, because this is the direction where x1 is equal to x2. So this direction is the direction of change of lighting. And you also have some points over here for those images that have an edge. Now, if you, for every data point, you subtract x plus y divided by 2, you get this histogram here, right? Now, what happens if we apply our models to data that is preprocessed in these two ways? So here we have a model that captures only pairwise correlations like POT. Basically, it doesn't have the mean latent variables. It's like the model that they described, but without the mean latent variables. And you can imagine that a model like this could use the covariance latent variables in this way. So let's take the 2-pixel image example. If you have one latent variable, what you could do is to associate one Gaussian that is very tight at the origin, that is the blue one here, for the images that are smooth. So in that case, you can associate to that the state equal to 1. And you can flip the state for the latent variable to represent the other covariance. And the other covariance can be one that is elongated along the anti-diagonal to represent images that are not smooth, for which x takes the opposite value of y. And basically, by using this mixture of Gaussians, one that is very tight at the origin and the other that is elongated along the anti-diagonal, you can fit very well this kind of distribution. And indeed, if you apply to real image patches such a model, you find that the samples that you generate from the model have some structure. Now, what happens if you instead don't subtract from every input data point the mean? So if you just take your cloud of data points and center it at the origin. What happens is that with one covariance latent variable, you are going to get one Gaussian that is elongated along the main diagonal to capture the direction of change of lighting. But then to capture the remaining data points, you're going to use a Gaussian that is spherical, that is not capturing the direction of anti-correlation, which is the direction that you're interested in, because it's the direction where you get a breakdown of smoothness, where edges occur, and that's the direction that you would like to model. And indeed, if you train a model on data like this, that is preprocessed in this way, when you generate, you get samples like this. So you are only able to describe the fact that image patches can have different mean intensity. But there is not any structure. While if you have also, if you model both the mean and the covariance, you can do a much better job. Because now, even if you have one covariance latent variable, now the mean can shift the covariance up and down. And now, in both cases, even if you have one covariance latent variable, you can represent well both kind of distributions. And indeed, if you train on real data and you sample from it, you get, in this case, patches with different mean intensity, but they still have some structure. So why is this important? Because overall, when you model high-resolution images, you cannot assume that overlapping patches have the same mean intensity, and you cannot not model the local mean intensity. So having a model that is able to represent both the correlation and mean intensity is important overall when you scale to high-resolution images, as we will see in one moment. For image patches, you can get away by just subtracting the local mean, and then you don't need to model the mean. Although if you do it, you do a little bit better. But if you don't do that kind of preprocessing, then modeling the mean intensity is very important. So far, we have considered the case where you take images, you crop image patches at random locations, and you model them independently. You may think that a way to extend this model to high-resolution images is simply by tiling the image with patches. This is not good. This is not a good idea because you would introduce strong tiling artifacts at the edges of this, at the borders of these image patches. So one way to deal with this is to say, I use a subset of the filters at these image locations. So I use, say, a green filter at these image locations, right? And I use another set of filters, these red filters, at these other image locations that also tile the image, but they have a slight offset compared to the green image patches. And because there is this offset, these red filters will compensate for the tiling artifacts of the green filters, and so on and so forth. So this is how we extend the model to high resolution images. Basically, we have a subset of the filters that is used to tile the image, another subset of the filters that also tile the image, but with an offset, and so on and so forth. And this idea came from prior work by Carol Gregor and Jan LeCun, and more recently there is work also by Kwok Lee that has a similar idea. So now, what happens if we generate from, so we can train on high resolution images now, not just on image patches, and we can generate images after training on these high resolution images. And before I show you the samples that we can generate, let me show you what other models like standard baselines do. So this is a sample from a Gaussian model, and this is from a model that, so basically, imagine that you do a Fourier transform of images, and now you try to model each Fourier component independently. You fit a Gaussian to the marginal distribution of each Fourier component. Well, here you do a wavelet decomposition, and then you try to model each coefficient of the wavelet decomposition independently with the Gaussian. And so then you can draw samples at random for the coefficients, and then generate and see what these things look like. And what it looks like is that in the Gaussian case, you get clouds. So you are able to capture the power, but not the phase of images. So all the structure is lost. In the case of the wavelet decomposition, you get some structure, but it doesn't look at all very natural. Below here, we have samples from more sophisticated models. This is a pairwise Markov random field. So it's like the model that I described, but without latent variables. And this is from a product of student T that is called field of expert, because that's what they call when they extend to high resolution images. So this is like the model that I proposed, but without mean latent variables, just the covariance latent variables. And as you can see, it barely has any structure. It barely looks like marble. It doesn't look like a natural image, a photographic image. And this is a sample instead from the model that I described. The resolution is about 200 by 200 pixels. And you can see that you have smooth regions and sharp boundaries that are pretty typical of natural images. Of course, it doesn't look supernatural either, but it is a step ahead of the previous models. And you can imagine it's a pretty tough problem because you are sampling from a very high dimensional space. It's pretty tough to start from random and go in a place where there is actually some structure. This is another sample, So now the question is, how can we improve upon these results? And the title of my talk was Deep Gated MRF. And so far I've been talking about gated MRF. So the solution is going deep. So adding layers to capture more long-range dependencies between pixels. And so basically we have latent variables, mean and covariance latent variables. That, so given image, we can estimate the expected value of these latent variables, and we can use those as input to train another layer on the top. And in the experiments that I did, I simply used binary RBMs. So the simplest possible probabilistic model. You are very familiar with RBMs, I assume. That's the energy function of an RBM, and these are the condition distribution that you need to use to sample from it. And basically, after training, what you do, given one set of variables, you sample the other by simply computing this quantity and then drawing a sample, a random number between 0 and 1, and then you draw a sample from Bernoulli. And then given this, you sample that, you do this for a long time, and time to time you can use the condition distribution over the pixels, which was that Gaussian, multivariate Gaussian distribution, to show what these samples higher up means. And if you do that, if you have 3 layers, then you got samples that look a little bit more realistic. They look like these things, this thing, this thing. So you got longer range, like longer structure. It's more coherent. There is more variation on mean intensity. And this is like the overall panel comparing different models. So we went from something like this to something like this. So that's the progress that we did in generating natural images. The other thing that you can do after you train this probabilistic model is to use the energy function to score images. So we cannot really compute the probability of one image because we would need to estimate the partition function. However, what we can do is to use the energy to compare images, because if you take the difference between the energies and then you take the exponential, is equal to the log probability ratio between the 2 images. So after training, you got that, fortunately, photographic images have much lower energy or higher probability than random images. That's not surprising because we train for that. If you flip the image left to right, it turns out that the energy stays the same. However, if you flip the images upside down, then it turns out that images that are upside down tend to have higher energy, to be slightly less likely than photographic images. And that's pretty interesting because the filters are local. However, the model, by looking at many, many images, figured out that lighting is more likely to come from the top. And why do I say that? Because if you take those images for which the energy gap is higher, and you average that those images, you get this image. And you can see that these images have in common the fact that the top is brighter than the bottom. So the model figured out by itself, by just looking at many, many images, that the top of the image tend to be brighter than the bottom. That's kind of interesting. So far, it's all about generating images. It's kind of a way to interpret what the model has learned and what the model was not able to learn, because from those images, they don't still look very photographic. They lack texture, they lack, you don't see parts of objects, right? Yes?
Do you use also this tiling for generation or only for learning?
So the way that you sample has to be consistent with the way that you train. So in order to generate high resolution images, I train by using local filters and tiling the image and using filters that offset each other. And when I generate, I use the same model, I use the same sampler that I described earlier, the hybrid Monte Carlo. I start at random, and using the same parameters, I do a random walk in input space, and eventually after a warm start, I get to those samples that I shown.
The problem with generation is you take Monte Carlo samples, right? It doesn't necessarily imply that these tiles should match, because the tiles overlap, right?
Yeah, but in the energy function, you have terms that depends on each filter response. And therefore, because the hybrid Monte Carlo sampler takes the derivatives of the energy function, so basically the energy function makes sure that all patches, even though they overlap, are consistent with each other. So an interesting thing, now you remind me, is that one advantage, maybe speakers later on can debate on this, but one good thing about MRFs, undirected graphical models, is that the way that you sample is, if you think about doing Gibbs sampling, you iterate many, many times. You don't have a prior. The prior is very complicated. You cannot write it down. If you have a directed graphical model, you would sample from the prior and then generate down. Now, the sampling from the prior can sample things that are not consistent with each other. While here, my prior is very complicated. So I need to do many, many steps to generate a sample. And I need to iterate many times to generate, to do my random walk. And that iteration makes sure that things become consistent. So generation is a nice thing to interpret the model, but of course, we can use the model also in practical applications. And so, for instance, we can use the latent variables as features, as the features that you would compute by using any sparse coding method. So in this example, I use the latent variables to replace shift in a scene recognition pipeline. So there is a paper in 2006 by Svetlana Lazarnik where she introduced this data set. This is the 15 scene data set. It has 15 categories, 100 images per class in the training set. And you got bedroom, suburb, like images like this. And what she did, basically, she took the image and then she extracted shift descriptors on a regular grid, and then she used a spatial pyramid to compute histograms of these descriptors. Well, actually, she ran k-means first, and then she do the histogramming on the k-means descriptors, and then she ran some sort of SVM to do the classification. And basically, I took her code, just replaced the shift with my latent variables, and basically got very similar results. So this is just a way to say that these features are trained in a totally unsupervised way, but they can be used as generic descriptors for images. You would hope they would do better than shift. You may do better if you actually backpropagate through them, but I didn't do that. But usually that's what happens. Another application where this model can be used is image denoising. So there are many kind of noise that you may want to consider. Actually, those that are more useful are those that you never find in scientific papers, like photographic noise when you take a picture in the dark. People usually use Gaussian additive noise, where for every pixel you add some noise independently from the other pixel from a zero mean Gaussian distribution with a certain standard deviation. And so this is an example of an image, and this is the noisy version of it, where I add Gaussian noise with standard deviation 20 after you normalize the image. And basically, figuring out this image from this image, so this is your observation, and what you wish to recover is the original image. Now, this is an ill-posed problem because there are many images that can produce the observation. So what you need to do is to constrain the optimization problem. And the way that you constrain it is by exploiting the prior that you learn by looking at many, many images and by learning the statistics of natural images. And so in a Bayesian setting, you know that some additive Gaussian noise has been added, so that gives you the likelihood, which is a quadratic term, where n is the noise observation, x is your estimate. That's the likelihood term. And then you have a prior term, the p of x, that comes from your model. And if you use Bayes' rule, then in the log domain, these two terms sum up. And now what you can do, you can either compute an expectation of what is the probability of the true image given the noise observation, or you can do a map estimate. And if you do a map estimate, then it means that in the log domain, you need to compute the mean of the sum of these two terms, where f of x is the one that I described this morning, is that funny nonlinearity that depends on the square filter outputs, plus the mean terms too. So if you perform this optimization, then you do a pretty good job at denoising. And the PSNR, which is the peak to signal noise ratio, which is something like the SNR, that depends on the mean square error between your estimate and the actual true image. The PSNR increases by quite a bit. But if you compare to state-of-the-art methods, it is actually, state-of-the-art method is 31 decibel on this image. And the reason why we are not doing so well is because it over-smooth. So our prior thinks that images should be smoother than what they actually are. And if you look here, perhaps you are too far to see, but basically what we are missing is this texture, the stripes here. Those are missing a little bit. So what we can do to improve the model is then adapt the model to this specific image that we are denoising. And so what we do is, given the denoised image, we can train on that denoised image. Okay, so that now the parameters are gonna fit to the particular image that we want to denoise. And then after we do this for a little bit, we solve again this optimization problem to denoise. So it's an iterative process where you can imagine that now, because you adapt the filters to this particular image, and because you are seeing some stripes, then you get the gabors that try to tune for these stripes. And here that you were missing stripes, they are gonna stick stripes over there, right? And indeed, the PSNR goes from 28 to 29.2. So we got a boost of improvement. But it is still a bit far from state of the art on this particular image. And so what I did was to interpolate this model with a non-parametric model. So the best denoising methods on images that have strong texture, like this one, are non-parametric. For instance, one of them is called non-local means. In non-local means, it's very simple. For every pixel that you want to denoise, you take a patch that surrounds it, and then you look in the image for other patches, and you compute the Euclidean distance between your patch and this other patch. And that Euclidean distance is gonna basically give you the weight that you use in representing the patch that you're interested in, because the patch that you're interested in is going to be a weighted sum of all these other image patches that were in the image with the weights that depends on the distances between these images, right? And so this is really great for images that have a strong texture, because basically you're going to take into account similar texture in the image. And if you do this sort of interpolation, then we got to state of the art. And basically, if you look here, now the stripes are really perfect. And not only, but where no local means would fail, which is these smooth regions. Now, because our parametric model is very good at capturing the global structure, we do well both in the smooth part as well as in the texture part. So again, this is, I think, a nice example where you don't want to stick to one model, but you want to leverage the strengths of different models to do well at your task. Another application that I would like to talk about is recognition of facial expression under occlusion, where the generative ability of the model is really leveraged. So a colleague of mine put together a data set that has 100,000 unlabeled images of faces that are aligned by the eyes with the standard toolbox. And we have 4,000 images that are labeled with the facial expression. For instance, here we have a few examples of anger, disgust, fear, happiness, neutral, sadness, surprise. So we have 4,000 images that have a label that is 1 of 7. And the resolution is 48 by 48 pixels. And basically, I train a 4-layer model that has this gated MRF at the first layer and then RBMs at the 4 layers above. And you can see that if you apply a linear classifier on the raw pixel, you get slightly above 70%. A Gaussian SVM does slightly better. If you use a very large Gabor filter bank, and then you take the square root of the sum of squares of quadrature pair Gabor filters, and you do PCA, and then you use a linear classifier, you get to 80%. If you do sparse coding, it's not very good. You got 75% or so. And if you use our model, we got 82.5%, and we didn't do any fine tuning. But now what is interesting is that you can generate from this model as well. So the way that you generate is always the same. You run the Gibbs sampling at the very top layer, and then you back project in image space using the chain of condition distribution over the input at each layer. And here we have a few samples from the model. And this is a video showing you the sampler in action. So every frame is a sample from the Gibbs sampler. And you can see that by sampling on the very top and projecting down in image space, you smoothly transition from one phase to another with different also lighting condition, different expression. And it's nice to see how it morphs from one individual to another. So I think in a little bit, you should go in a nice mode where it is, let's see. I guess my computing presentation mode is a bit slow, so it takes time to go over it. But in a little bit, it's going to start smiling. So this is the smile mode. So it's happy. Yeah, so nice. Anyway, so this is just a demo to show the sampler what it does, right? And now I will go in another mode and so on and so forth. But what is cool about this is that you can use the generation ability of the model to cope with occlusion. So let's say that the input image has some part that is occluded, and let's assume that you know which part is occluded. Now what you can do to extract the features is you go up, as you did before, to extract the features, and then you go down to generate. But now when you generate from the gated MRF, you not only condition on the first layer hidden units, but also on the pixels that you know that are not occluded. Now, when you have a Gaussian distribution, you condition on some variables, the condition distribution is still a Gaussian, so we know how to sample from it. And if you keep repeating this process, eventually you're gonna infer what are the missing pixels. And so we have a few different types of occlusions. So on the first row, we have an example of images that the model has, and individuals that the model has never seen during training. And on the second row, there are images that have been occluded at the eyes, on the eyes, right? And below here, there are the restored images where we guess what the eyes are. And this is another example where we occlude the mouth, the right part. See, in some cases, it does a very good job. In this case, not much. The mouth is difficult for some reason. There is a lot of variability there. Top part is creepy. It's evil eyes, good for Halloween. The nose is easy. 70% of the pixels at random. This looks very tough for the human eye, but actually it's very easy for machines. Even linear interpolation does well in this task. And so basically here we have a zoom of what happens. So if you have the image, you occlude the right part. So this is the best example that I could find. So this is, for the sake of presentation. This is the first layer. So if you go up the gated MRF and immediately you reconstruct, you barely do anything predicting what is the missing part. If you go up 2 level and then down, you start seeing some sort of eye, right? Now, if you go up 3 layers and then go down, it is slightly better. 4 layers, you start seeing the mouth. You repeat this process 10 times, it's remarkably good. So the point here is that by going up, you see more and more context, and you can predict more about what is missing. And by repeating this process, eventually it fantasizes things that are likely. And now you can use this for recognition, because now say that you have a training set where images are occluded, and you know where they are occluded, and also on the test set you have images that are occluded. You do this process of imputing the missing pixels, and then given those images, you extract the features, and then you can give those features to any classifier. In this case, I use the linear classifier. And so on the x-axis, we have the different types of occlusions, and on the y-axis, the recognition accuracy. And the blue bar is the accuracy of our model. And here we have a few different baselines, also sparse coding. So we do consistently better than other approaches. So let me conclude with an experiment on for speech recognition, how we can use this model for speech recognition. And by the way, speech recognition is actually the leading practical application of deep learning nowadays. At the last conference at ICASP, there were 15 deep learning papers. It's really a big thing, and all the major labs in the industry that do speech recognition, like IBM, Google, Microsoft, they are all using neural nets with many layers for their acoustic model. So speech recognition, what is speech recognition? It's just an image where the x-axis is time and the y-axis is frequency, okay? And so basically, from my perspective, I just take a small patch and then I use the same technology to extract the features. And basically, after doing pre-training, what you can do is you can discriminatively try to predict the states of the HMM, okay? And then once you have the state of the HMM, you can run Viterbi decoder and the transducers to figure out what is the what has been spoken. So this is basically the performance of different methods on the TIMID dataset, which is a standard benchmark for predicting the phones. And basically, this was a result published a couple of years ago. It was a real breakthrough because we were able to improve by a large margin the best previous method. And in speech recognition, this is a very big improvement, because if you consider when these results were published, you realize that pretty much the best methods were published more than 10 years ago. And there has been very little progress in improving the acoustic model until deep learning came. And now we are all using deep learning for that. Okay, so basically today I've been talking about unsupervised learning. In particular, I have been talking about using a generative model, so a probabilistic model for learning representations of images, where the first layer is this gated MRF, and the key idea is that we have two sets of latent variables, those that set the mean intensity of pixels and those that control the dependencies between pixels. And it does a better job at generating natural images, and it can also be used in a few different applications for vision, but also speech recognition. So that's it. Thank you.